Thanks for accepting our paper and giving us a chance to present our work in this workshop. I'm Kavya Manohar. I'm a research scholar at College of Engineering, Trivandrum, Kerala, India. Uh, Myself, with my supervisors, Dr. A.R. Jayan and Dr. Rajeev Rajan, are working on various linguistic challenges associated with the automatic speech recognition in Malayalam language. So Malayalam is our native language. It's the official language of the Kerala state in southern India. Uh, it's it's a Dravidian language with about 38 million native speakers, but still it is under-resourced in various aspects. Apart from this under-resourced nature, Malayalam is also highly morphologically complex in nature. The morphological complexity of Malayalam produces a lot of challenges in the task of automatic speech recognition. We try to solve those challenges by attempting to use subword tokens instead of word tokens in the automatic speech recognition system architecture. So before we go into details, let me introduce the automatic speech recognition system architecture we are using. This is the architecture commonly used for most of the low and medium resource languages for speech recognition. The system is called a hybrid architecture in which we have three basic components called the acoustic model, the language model, and the pronunciation lexicon, which are combined together in the form of a weighted finite state transducer. The acoustic model is basically a learned representation of mapping between the speech features and the phonemes of the language. The pronunciation lexicon is basically a dictionary that contains all the words we intend our ASR decoder to recognize, along with their pronunciation described as a sequence of phonemes. In a continuous automatic speech recognition system, what we expect at the output is a sentence or a sequence of words. So in order to predict the word sequences correctly, it's always good to have a language model. A language model is a learned representation, which is learned from a huge corpus of text, which learns the probability distribution of occurrence of words or word sequences given a previous n number of words. If it is, if the probability distribution is known based on previous one word, we call it 1 gram language model. Previous one word, we call it bigram language model. Previous two words, then it's called trigram language model, and so on. So basically, combining all these things, we make an ASR decoder. So what is the challenges a morphologically complex language like Malayalam face here? So morphological complexity is characterized by formation of longer and newer words in the language by agglutination and inflection. New word forms can be formed from existing word forms without any grammatical limitations. So practically, it is impossible to have all possible word forms in a finite or a static pronunciation lexicon. Again, when there are possibility to form large number of rare words in the language, then it's difficult to learn the probability model of language modeling. That is, data sparsity issue comes into the situation. So how to solve this issue? So these are the challenges I mentioned: the finite lexicon and the possibility of infinite vocabulary. Then the problem of out of vocabulary words. That is, we cannot detect a word that is not present in the pronunciation lexicon. So if a new word is occurring in our test speech, then it is called the out of vocabulary word, and it cannot be detected by the decoder. And the third problem is the data sparsity in language modeling. The solution, which is widely being used, is the development of an open vocabulary ASR. In an open vocabulary ASR, the acoustic model part remains the same, but pronunciation lexicon and the language model are structured a bit differently. Instead of word-based pronunciation lexicon, in an open vocabulary ASR, we will have subwords as entries. Subwords are basically pieces of words that can be glued later to form the full words. So in a subword pronunciation lexicon, we will be using subword tokens. Specifically in the experiments we describe here, we use syllable tokens as entries in the pronunciation lexicon. So when you are using a syllabified pronunciation lexicon, you will need to train the language model not on sentences which are tokenized as words, but tokenized in the form of syllable components. So we will see how we performed that syllabification and how it improved our ASR system. So this is an example of sentence from the text corpus used for language modeling. On top, you can see a word level tokenized sentence, and the same sentence is tokenized as syllables in the second sentence. You can see the marker sign plus to indicate that particular syllable is not an end of the word. That means if you see a plus sign, it indicates some other subword token has to come after that to complete a word. So that plus sign is used you can look at this word recovery module. The plus sign will be removed and the next subword will be joined to the previous word to form the full word in an open vocabulary ASR. So this additional module of word recovery is essential in an open vocabulary ASR. So this is the text corpus for language modeling. And regarding the pronunciation lexicon, which I call PL, on the left, you can see the word pronunciation lexicon. You can see Malayalam words along with its pronunciation described as phonemes. And on the right side, you can see the syllable pronunciation lexicon, where you have syllable subwords as the entries in the lexicon. Even though in the example I show here, you can see the number of syllables is more than the number of words in the corresponding lexicon. But in practice, when we have when we have a word pronunciation lexicon of about 25,000 words, the number of unique syllables in those 25K words will only be some 3,000 or something. So you can effectively reduce the size of pronunciation lexicon by using syllable tokens. We will see about it soon. So this is the example of pronunciation lexicon in word token form and syllable token form. The acoustic model, which is a common component in both open vocabulary as well as closed vocabulary ASR system, it's basically a mapping between the acoustic features and the phonemes of the language. So the syllable tokenization algorithm we are using is essentially our based on our previous work Our previous work was the development of a Python library ML phone, which basically is a bidirectional grapheme to phoneme converter for Malayalam language. So in that library, we have a module for syllabification, and we use that algorithm to syllabify the text corpus used for language modeling. So given this background in mind, we define our objectives of the experiment as to study the impact of vocabulary size, ASR error rate, automatic speech recognition error rate, and the model memory requirement while using syllable subword tokens when compared to word token based ASR. So how did we perform the experiment? So in order to develop an automatic speech recognition system decoder, you have to train the acoustic model as well as the language model. To train the acoustic model, we need an annotated speech corpus. In our experiments, we used publicly available open licensed speech corpora available in Malayalam for training the data, training the acoustic model. Then to test the ASR we developed, we use 3 different tested data sets. So let me explain. The top 2 rows show the training data sets, and the bottom 3 rows show the test data sets we use. For training, we combine train 1 and train 2, which is about 18 plus hours of annotated read speech corpora recorded in studio environment. The test data sets T1, T2, and T3 are from different corpora. We are not combining it because we want to test the effectiveness of our ASR decoder we developed and how different test data set domain affect the decoding. So we keep the 3 test data sets separate for testing, and we'll see analyze the result for each of these test data sets separately. You can see the third data set for testing T3 is actually not studio recorded, which is drastically different from the training data set, and it has its impact while decoding. The acoustic modeling, we use Kaldi ASR toolkit for acoustic modeling. As acoustic features, we use MEL frequency substral coefficients, or MFCC, and I vectors, a set of features extracted from speech frames to train the acoustic model. For acoustic model training, we use time delay neural network recipe available in Kaldi ASR toolkit. And speech data sets, text data sets, we use all the transcript of speech available for training, and we additionally expand the text corpus with SMC text corpus, and together it constitutes about 205K sentences. We tokenize it as words as well as syllables and use it to train the language model. Language modeling is trained using SRI-LM toolkit with n-gram orders of 2, 3, and 4. We will see the impact of n-gram orders as well. So pronunciation lexicon. So primarily, we create the pronunciation dictionary. To begin with, we create the first pronunciation lexicon, word pronunciation lexicon, PL1 of W with about 25K entries. And corresponding to that word lexicon, we create the syllable lexicon PL1 of S by syllabifying every word in PL1 of W and taking the unique set from that. So corresponding to the 25K words in PL1 of W, there are about 3K words in the syllable lexicon. We expand the word lexicon to see how the expansion of the lexicon affects the out of vocabulary word rate of the test data set. So we incrementally rise the number of entries in PL1 of W and obtain the subsequent lexicon PL2 of W, PL3 of W, and PL4 of W. So to develop these, we incrementally add more on words to the first lexicon. And corresponding to every word lexicon, we create the syllable lexicon also. So the number of lexicon, words in PL2 of W is created by adding words of at least 5 occurrences in our language model training corpus to the original lexicon. So PL3 of W contain all words in the text corpus that has at least 4 occurrences, and PL4 of W has all words in the training corpus with at least 3 occurrences, and so on. And to create the pronunciation, we use our previously created tool MLFont Python library to generate the pronunciations. So with the common acoustic model and word-based LM, combined with the 4 different word level lexicons, we created 4 word-based ASRs. With the common acoustic model, syllable language model, and the 4 different syllable pronunciation lexicons, we created 4 different syllable token-based ASRs. So in total, we have 8 different ASR models which are evaluated on different test data sets. So going to our results. So as expected, lexicon size affects the OOV rate. OOV rate is out of vocabulary word rate of the test data set. We have 3 different test data sets, T1, T2, and T3. They differ in their OOV rates. The first test data set T1 has less than 6% OOV rate in PL1 of W, and it reduces to less than 1% in PL4 of W. You can see the blue bar, and can go to the orange bar. It is the OOV rate in T2, that second test data set. It ranges between 28 to 14% of OOV rate when we move from the first lexicon to the 4th lexicon. And you can see the green bar of OOV of T3. The OOV rate in T3 is very high, between 44 and 58%. It means half of the words presented to the decoder by the test set T3 is out of vocabulary. That is, those words cannot be recovered by the decoder. Additionally, test set T3 is noisy. So we expect the worst performance of our ASR on the third data set T3. Now let us see the results one by one. So before going to the results, the evaluation metric for our data, our ASR is word error rate. It is calculated based on the number of insertions, deletions, and substitutions that happen at the decoded output when compared to the number of words in the true ground truth transcript. So word error rate is the sum of all insertions, deletions, and substitutions happening in the decoded output to the ground number of words in the ground truth transcript, and it's often represented as a percentage. So lower the word error rate, the better is the performance. So this is the result of word error rate on the test data set T1. As you can see, test data set T1 has very low OOV rate. When the out of vocabulary rate is very low, the performance of word level ASR, the first 4 bars, set of bars represent word level ASR. They have a lower word error rate, which means in this situation, the syllable subword tokens are not advantageous. The best word rate given by the word level model is 9.8%, while the best word rate given by the syllable token based ASR is only 12%. So subword tokens are not advantageous on test set with low OOV rate. Coming to the test set T2, which is a medium OOV test data set, between 14 to 28% is the OOV rate of this data set. As you can see, the syllable lexicon with higher order language model, that is 3 gram and 4 gram, perform better than corresponding word level lexicons. So syllables perform at least 10% better than the best word-based lexicon. For medium OOV test data sets, they are definitely advantageous. Syllable subword tokens are definitely advantageous. Coming to the third test data set T3, which is an out-of-domain test data set recorded in a natural and noisy environment with about half of the words OOV. We have a very poor performance on with word level lexicons, about 88% of word error rate, but the word error rate reduces to about 78% using syllable lexicon. Even 78% is not an acceptable rate in case of an ASR, but that's the state of Malayalam automatic speech recognition as of now. So on open domain text with a lot of noise, the performance is poor, but syllable subword model performs better than the word-based model by 7 or 8% in this case. One more thing to be noted, the n-gram order has little effect on word level lexicons. You can see 2 gram, 3 gram, and 4 grams perform equally well for word-based model, but for syllable level lexicons, n-gram order 2 performs very poorly, but higher order n-grams perform better. And regarding the model size, with increase in n-gram order, in general, the total size of the ASR decoder also is increasing. In general, word level lexicons have higher model size than the syllable level lexicons. The size we present here is of the ASR decoder, the final ASR decoder, which is composed of the acoustic model, language model, and the pronunciation lexicon in the form of a weighted finite state transducer. That FST size is described here. So syllables with n-gram order 2 has very low model size, but its word rate is also poor. But at n-gram order 3, even though the size is increasing than n-gram equal to 2, it is still much lesser than the model size of word level model, and the performance in terms of ASR is also much better for medium and large OOV scenarios. So coming to the conclusion, we present our first work, and this is a first attempt in the usage of a linguistically informed token. That is, here we are using syllable subword tokens in Malayalam ASR, and in comparison with word baseline, it shows the usage of syllable subword shows a reduction in word rate on medium and large OOV scenarios, a reduction in model size for n-gram order 4 or below, as we see in those graphs, and it has a reduced lexicon size. But in low OOV test datasets, where the test datasets are almost the same domain as the training datasets, then syllable subwords are not as advantageous as word-based ones. And we are currently planning to implement other subword tokenization mechanisms in Malayalam and experiment their impact on the Malayalam ASR. So here are our major references. And thanks for listening.